I'm Donna Ball. I'm the lead scientist for the South Bay Salt Pond Restoration Project. And I'm here with Dave Halsing, our executive project manager, and our project partners and our project members of our project management team. And we're going to host the first of what we hope are going to be a running series of monthly lunchtime science speaker presentations. And we're gearing these towards informing the restoration project science questions, and then particularly our adaptive management questions. We also hope that these are going to be presentations that are of interest to the larger science community and to the public. So this talk pertains particularly to informing two of our adaptive management questions and targets that are related to sediment, including the targets that are that the project would not result in long-term net loss of vegetative marsh throughout the South Bay, and then that the accretion rate of our restored ponds will be sufficient to reach vegetation colonizations. So our first speaker in this series is Kevin Buffington of the US Geological Survey, and he's going to be giving a talk on modeling sea level rise vulnerability for tidal wetlands of South San Francisco Bay. And he will address particularly marsh resilience and accretion of South Bay marshes that will help with these questions that we have about the project. So this is work that's been funded in two parts. An earlier study by USGS on the vegetation component was funded by the Don Edwards National Wildlife Refuge. And the second study using about the warmer framework and SETs has been funded by the South Bay Salt Pond Restoration Project through the California State Coastal Conservancy. So Kevin's here today. He's a biologist with the USGS Western Ecological Research Center. And research interests include field observations, remote sensing, and numerical models to assess tidal wetlands vulnerability to climate change and especially to sea level rise. So in recent years, he has continued development of the warmer modeling framework, wetland accretion rate model of ecosystem resilience. And I'll have you say that like 5 times, Kevin, which we'll hear about today. So he has ongoing projects that apply this framework across the country, including a countrywide vulnerability assessment and international work in Micronesia and in New Zealand. And he works remotely from Colorado and enjoys, like a lot of us in the outdoors, camping, hiking, and photography. And so with that, I'll let you take it away, Kevin.
Very good. Thank you, Donna. And thank you all for taking time out of your busy day to hear a little bit about this project and our assessment of wetland vulnerability across South San Francisco Bay. Let's see, forward. So I do want to start by acknowledging our project team, specifically Karen Thorne, also with USGS, and our co-PIs, Rachel, Peter, and Tom. And want to highlight also field and lab assistance by James, Desmond, and McKenna. And Donna already mentioned our funders. And so, yeah, this is kind of a phase 2 of our project to understand vulnerability across South Bay wetlands. So very quick background. Don't want to belabor the points, but climate change is fundamentally altering our environment. Storms are more intense, sea levels are rising, and projections from global models mean that we have to try to anticipate how climate change will impact the ecosystems that we're entrusted with managing. Now, for tidal marshes, this means collecting a lot of baseline data to understand historic and current conditions. We can use experimental approaches as well to help inform, gather fundamental information about the underlying processes, as well as determine physiological limits for key species. We're continuing to build our understanding of the mechanisms that control key processes, such as accretion and compaction. And these allow us to develop numerical models that can take the projected changes in climate or sea level rise and assess how the ecosystem may respond. Well, these modeling tools can also be used to explore various management actions, providing valuable information for resource managers. So study is focused on Don Edwards National Wildlife Refuge. They manage over 3,000 hectares of tidal marsh across South San Francisco Bay. These marshes are generally high in the tide frame, with marsh plains dominated by pickleweed, and there's California cordgrass found along the marsh edges and along channels. These marshes are critical habitat for all endangered species, including the ridgeways, rail, and salt marsh harvest mouse. Marshes also provide key protection for storms along the exposed shoreline, and are an important sink for carbon. Now, due to the intense urban development and the levee network that surrounds these marshes, there's really no capacity for these marshes to migrate upslope, like in some places. So really their only path for long-term survival is vertical accretion. Our team has been working at down inwards for about 8 years, gathering information needed to produce site-specific projections of marsh elevation with sea level rise. And of course, as this group is keenly aware, there's extensive restoration efforts all across South Bay through primarily passive restoration efforts, returning tidal influence to these retired salt ponds, allowing natural processes to build marsh elevation. Once completed, this effort has the potential to create about 6,000 hectares of tidal marsh, although there are really important outstanding questions about, is there enough sediment coming into the bay and into these restorations to support tidal marsh both now and with sea level rise. So healthy tidal marshes, mature marshes, are capable of tracking changes in sea level through biological and geophysical processes, things like root growth and turnover, litter deposition, and slow rates of decomposition. These marshes can build soil elevation over time. Across South Bay in particular, sediment deposition facilitated by tidal flooding is really the predominant mechanism for marsh accretion. If there is sufficient sediment available, marshes are able to keep pace with relatively high rates of sea level rise, given there's a positive feedback between time flooded and sediment deposition. However, without a consistent source of sediment, accelerating sea level rise is likely to outpace accretion processes and lead to conversion potentially to unvegetated mudflat. So the goals of our study are to, or I guess are pretty straightforward, right? First, measure marsh accretion rates using historic data derived from soil cores, as well as install surface elevation tables. Next, use these information to calibrate a model of marsh elevation or evolution, specifically the warmer framework. We then use warmer to project marsh features under a range of sea level rise and sediment scenarios. And then since we had the data, we also calculated the amount of carbon that's currently stored across Don Edwards marshes. So this is a conceptual framework for the latest version of warmer, it's kind of version 3. It was just released or accepted to Estuaries and Coast last month. And the paper and code will be available soon. So warmer is a process-based 1D soil cohort model that captures the dominant above and below ground drivers of elevation change. So I'll quickly step through this figure, give you a sense of what's going on. Really, everything in the model is relative to mean sea level, which increases through time given a provided sea level rise scenario. The model can handle any number of species, so multiple marsh species, for instance, as well as seagrass or mangroves. The probability of occurrence is defined by a species niche, here defined by flooding tolerance. Species cover is converted into above and below ground biomass. Roots are split into various size fractions, each with their unique turnover rates. As organic matter processes kind of break down, organics are split into refractory and labile fractions, and then subject to decomposition. Mineral sediments are deposited on the surface according to a submodel that's based primarily on tidal flooding depth. So then every year, the total soil volume is updated, and in turn, the elevation relative to mean sea level is updated. So briefly, there are some of the key improvements on this version are the ability to model mangroves and account for root volume explicitly. Cohort volume is now controlled by kind of improved model of porosity, which allows a finer control over compaction rates. And then rather than tracking material using annual cohorts, which is the case in prior versions, this version uses depth cohorts, which is done to allow for easier integration with hydrodynamic models and being able to simulate erosion more effectively. So I do think it's important to understand some of the limitations and assumptions within 1D models like this. So in general, they assume that vertical processes are solely responsible for long-term marsh evolution. So this means things like edge erosion are not considered. Generally, we use soil cores from the marsh plain, far from the channel edges or the edge of the marsh, so that the model is simulating marsh plain dynamics. If we instead use model calibrated with cores from right next to a channel, we're likely to show much longer resilience to sea level rise given higher rates of sediment deposition. But that's not necessarily representative of the marsh as a whole. Warmer assumes that marshes are net depositional. So again, surface erosion is not simulated. In this version, plant species are defined by an elevation niche as well as competition for space with other species. For now, things like salinity or facilitation are not incorporated in the model, but I do have some work ongoing in those areas. As I mentioned at the top, this modeling effort is leveraging some earlier work across Don Edwards. So we surveyed about 2,800 elevation points, 1,300 plant surveys all across different parcels around Don Edwards to really help kind of capture current conditions. We also monitored water level and salinity for about a year. So all these data together were key for parameterizing the model. So using that RTK elevation data, as well as available LiDAR data sets from 2010 and NAPE imagery, we generated a bias-corrected DEM that helped improve the accuracy of kind of the initial conditions by about 60%. So this data set provides the initial marsh elevation for warmer. And if you're all interested, this product is available on ScienceBase. Bias corrections for South Bay, but also really all of San Francisco Bay and across the Seward Marsh as well. So to understand soil characteristics and historic accretion rates, we collected 24 soil cores across 8 representative sites. So sites being across Greco Island, Dumbarton, Maury, Calaveras, Coyote Creek Lagoon, Triangle Marsh, Guadalupe Slough, and Laumeister. We process these cores for bulk density and percent organic matter using LOI, and been working on dating them using lead-210. So a bit of peek at some of these, what these data look like. Depth averaged percent organic matter was ranged between 11 and 14%. Really had relatively low variation down core, fairly consistent. We're still waiting on muffle furnace availability to finish processing some of these cores, especially at Coyote Creek. I anticipate probably a little higher percent organics there, given its more brackish conditions. But in general, fairly consistent and moderate levels of percent organic matter. Bulk density is where things get a little interesting. Overall, bulk density was really high, with depth and core average densities ranging between 0.76 and 0.94 grams per centimeter cubed. Now, just to give you a sense of this, compared to other places around San Francisco Bay, pulling data from John Calloway's 2012 paper, we find that, there's just relatively very dense soils, but still holding on to a fair bit of organic matter. Okay, and then since we have the data to do so, and John published a great correlation between carbon density and percent organic matter for the bay, we leveraged that in these soil data to estimate the amount of carbon stored in these marshes. And we found across these sites an average of 376 megagrams of carbon per hectare. And not doing a ton of carbon work, I was interested, like, okay, well, how is that a lot? What does that value mean? And looking at a recent global meta-analysis, puts this value at about the 86th percentile worldwide for carbon storage. So that's kind of interesting. Based on marsh area, so just scaling these values by about 3,000 hectares, estimate about 1.16 teragrams of carbon down to 1 meter. All right, so on to the dating. Again, here's a distribution of soil cores that we sampled. And these are the cores that we have so far been able to date, just 3 so far. Maui and Guadalupe Slough had reasonable depth profiles for lead 210, and a core at Triangle Marsh had a significant peak in cesium, which we can use instead of lead to determine an accretion rate. These data suggest rates of 2.1 mils a year at Maui, 3.7 at Triangle, and 5.5 at Guadalupe Slough. So these are the 3 sites that I'll show projections using warmer for, just these 3. So many of the soil cores processed so far could not really be used for lead 210. The radioactivity levels are just too low, and the depth profiles indicate mixing. The low activity levels aren't, I guess, super surprising given we just don't get much rain with our Mediterranean climate in the Bay. Another potential issue, the labs that we use to gather these data rely on gamma spectrometry for dating. It's possible that alpha spec might be more sensitive, might be more successful since it's more sensitive to lead 210. And then finally, the large, South Bay has really huge mudflats, and sediment is constantly getting reworked across those. And so it's possible that that's just going to be an underlying challenge dating with these methods, just with that the amount of mixing that occurs. So, however, despite these challenges, we're still going to try to date the remaining cores in our queue. About 10 left, I think. All right. So again, considering these issues, it's a good thing that I guess we installed some surface elevation tables with marker horizons. These were installed across 5 marshes in 2022. So we don't have quite enough data at these to inform the model yet, but in the next few years, we should be able to use these data for either calibration or alternatively validation of the model. All right, so switching now to model parameterization. From field surveys across Dunn Edwards, we generated an elevation niche for cordgrass and pickleweed. So the solid lines are the functional relationship between cover and scaled elevation, and the histograms are the relative distribution across Dunn Edwards. So these curves define the growth rate and distribution for each species relative to elevation. And then on the right are the species-specific calculations for biomass that account for the niche, flooding, or the relationship between flooding time and productivity derived from marsh organ experiments, and their respective root-to-shoot ratios. So the solid line is the above ground biomass, below ground is in the dotted line. So we used tidal harmonic constituents to calibrate the sediment deposition submodel for each site. The submodel accounts for interactions among settling velocity, tidal current velocity, and flooding depth. It's run using a constant SSC, suspended sediment concentration, but then that result is then scaled according to the sediment accumulation rate from the soil cores. So you notice that each site, their y-axis is different across the sites. And there's a different overall functional shape based on differences in tidal harmonics. Now, in general, I'm pretty skeptical of relying on a single core to calibrate a model that predicts the future, which is why we're still going to continue to try to date our existing cores as well as integrate the set data once we have a long enough record. So those caveats in mind, march forward with calibration. I used a 50-year hindcast to calibrate the rate of organic accumulation by adjusting the rate of decomposition. essentially, I'm attempting to recreate the last 50 years of marsh development. Across sites, there was pretty good alignment between the modeled and observed accumulation rates across sites. On average, over 50 years, accretion rates was about within 12% of the observed rates from soil cores, with a RSME of about 0.36 millimeters a year. And then these figures just show the depth profiles of organic matter and bulk density, the solid line being the modeled, and dots being from the soil cores. And overall, pretty good alignment across these different sites. All right. We simulated marsh evolution across 6 future scenarios. We had 3 sea level rise scenarios from the AR6 IPCC report. And these scenarios are based on global projections, but adjusted for local processes such as vertical land motion. For each of these sea level rise scenarios, we also ran 2 sediment scenarios. First being a historic scenario that used the soil core calibrated SSC value. And then the second scenario, assuming a 30% reduction in sediment availability. Now, conceptually, this is based on the reduction in sediment delivery through the delta, as well as an increase in sediment sinks caused by all the marsh restoration efforts that are going on. Now, this 30% reduction was selected as a reasonable value to explore model sensitivity. But if folks are aware of a more, I suppose, accurate prediction of sediment availability going forward, please reach out. All right. So now I do want to mention that, to date, observed rates of sea level rise across the bay have remained relatively slow, really near that long-term average of about 2 mils a year. So that's what this figure shows. On the right here are the sea level rise acceleration millimeters for each of the nonlinear sea level rise scenarios that I selected. So this dotted line, that's 2 mils a year. These scenarios are starting, in 2020 with rates of, between 3 and almost 5 mils a year. So, while I still, still use these projections since they're considered really the best available, understand that really the timing of marsh evolution with these projections might be a little faster than what will occur in the future. And just to highlight the point, I guess, we have not yet seen the rate of increase in sea level compared to other places. So for example, Chesapeake Bay and across Florida, I've already starting to see an uptick in the sea level rise rate. All right, on to some projections. The top panel shows mean marsh elevation relative to mean sea level through time for each of the 3 sites. And then the bottom plot shows proportion of cover for pickleweed in the solid line and cordgrass, the dotted line. And so I'm going to flip through and add different sea level rise scenarios to the plot. So starting with the intermediate scenario, the lowest scenario that I ran, but it's labeled as the intermediate sea level rise scenario. And we see that Guadalupe Slough and Triangle Marsh are both projected to be resilient and remain tidal marsh through 2100. However, Maury transitions to a mudflat by about 2090 after converting to primarily cordgrass. Under the intermediate high scenario, Guadalupe Slough is still projected to maintain as a tidal marsh. 50, and then to mudflat about 20 years later.
Kevin, could you repeat that last? You froze for just a second.
Sure. So this is under the intermediate high scenarios. Guadalupe Slough is projected to be resilient, transitioning to cordgrass in about 2060. But both Maury and Triangle transition to cordgrass between 2040 and 2050, and then to mudflat about 20 years later. Under the high sea level rise scenario, really all sites transition to cordgrass about 2040, and then to mudflat by about 2050. It's a really rapid transition. Okay, and now I'll just show this plot for the comparing the two sediment scenarios with about 30% less sediment available. All marshes transition to mudflat eventually, with the largest difference in projection being at Guadalupe Slough, just because they had the largest change in sediment availability with that 30% reduction. So again, more just to give a sense of the sensitivity of the model to various sediment loadings. All right. So considering those kind of issues, I suppose, or those considerations with the sea level rise projections, I also wanted to understand, what is the sea level rise rate threshold for these sites based on these calibrations. So ran this analysis using mean elevation and then a linear sea level rise scenario between 2 and 20 mils a year. And we assume that if the marsh is at least 50% vegetated after a 200-year run, it's resilient to that rate of sea level rise. So then we also tested both sea level rise scenarios, or both sediment scenarios with this analysis. So we found a pretty wide range in sea level rise rate threshold, ranging from between 6 mils a year at Maui up to 18 and a quarter at Guadalupe Slough. And this plot shows relative to those nonlinear IPCC scenarios, kind of the timing of those thresholds for each site. Kind of interestingly, I guess the analysis does show that even under this low sea level rise scenario that was modeled, all three marshes will eventually transition to mudflat as that rate is above the threshold limit for persistence. Switching to the less sediment availability scenario, not surprisingly, we see a pretty drastic drop in the threshold rate for sea level rise. And really it suggests that the accretional capacity is outpaced by sea level by about 2060 at all sites. Okay, so I want to summarize some of the key take-homes. First, we've found that soils in South Bay marshes are really dense, with bulk densities really surpassing really anything I've seen across the rest of the bay. Kind of key point, this recent SFEI report looked at how much sediment is needed to support all these restorations that are going on, as well as maintaining current marsh with sea level rise. And they used best available data, but there were no cores available for this far South Bay area. By plugging in our measured values, it just suggests that really there's a substantial underestimate in the amount of sediment needed to support these restorations. So we need more mud to take home. But again, because of these really high densities, carbon storage in these marshes is among the highest in the world, which is kind of surprising and but also really exciting. And I guess really just highlights the need to come up with innovative solutions to try to maintain them going forward with the kind of scary projections of sea level rise. We did have a lot of issues obtaining good accretion rates with radioisotopes, but the installation and maintenance of a robust Sept network that's been installed around the bay, this will really aid future efforts to assess vulnerability to sea level rise. The warmer projections of these three marshes suggest some resilience under that moderate sea level rise scenario. However, marsh loss does seem inevitable under higher rates of sea level rise and lower sediment availability. Transitions are really starting to form up around 2040 if these projections come to pass. Again, these results really highlight the need for innovative solutions to boost sediment deposition or sediment availability and keep increasing vertical accretion. Now, I do want to point out, as noted kind of at the beginning, warmer does not explicitly capture lateral processes. And these are probably pretty important, especially in South Bay. For instance, there's every summer, pretty strong sea breezes generate a lot of waves, and that process has resulted in pretty substantial edge erosion. Recent study at Whale's Tail found about erosion rates of about 1 meter a year. And so with that in mind, I've been working closely with Joel Carr at the Eastern Ecological Research Center to integrate warmer with a tide averaged hydrodynamic model that also captures wind wave activity in order to capture these key lateral processes that govern marsh evolution. So they're really trying to get at things like edge erosion, surface erosion, and sediment redistribution. So the framework is intended to be something of a Goldilocks model in terms of complexity, capable of generating results much faster than a fully resolved model like Delft 3D. But we intend to publish and release the model this year, so stay tuned for that. Okay, with that, thanks for your attention, and yeah, happy to answer any questions. Thanks.
Great, thanks a lot, Kevin. That's really interesting presentation. Ariel, I'm going to ask if you can see hands. For some reason, my screen isn't showing hands or chat right now. So,
well, not at this point, but let's encourage folks. We're transitioning to the discussion time. If you would like to raise your hands or just add comments in the chat, and Donna will be tracking them, and I'll let you know about hands. Any questions, comments? Go ahead, Christina.
Yeah.
Hey, Kevin, this is awesome. Thank you so much for presenting this. I wanted to know, there's so many interesting and spatially variable factors that go into this model. If you could pick like the top 3 metrics that you wish you could resolve in better temporal and spatial detail to refine this model, what would those be? Like, would it be additional, like more bulk density readings in different types of marshes? Would it be better tide data? What's on your wish list?
I mean, really, primarily, it's getting a sense of what's going on now in terms of vertical accretion, right? Like we had such trouble with the soil cores, which is unfortunate. So we do have sets out in a lot of these marshes now, and including in some of the restorations, and so that's really exciting. And we've done some targeted studies looking at mass deposition using sediment pads. So we have those data at Whale's Tail and Corte Madera and San Pablo Bay. But that is very intense kind of local spatial scale kind of information. Ultimately, I think things like a feldspar network, right, or a marker horizon network, where at least you're trying to get an understanding of the spatial and more temporal variation in surface deposition, and rely on occasional sets to capture the below ground processes. So that might be something. Yeah, I mean, of course, more resolution on tidal inundation, and really how to link changes in, I guess, sediment delivery, and I guess what that looks like going forward. So monitoring the key kind of smaller watersheds, and try to understand sediment processes going forward. Delivery.
Awesome, thank you.
I can see hands now. So Lauren and then Scott. Lauren, did you have a question? Okay, Scott, I'll have you go ahead then.
Okay, great. Thanks, Donna. And great presentation, Kevin. Thank you so much for this. And I'm sure you mentioned it, but I must have missed it. So the 30% decrease scenario that you ran for sediment supply. So did you just do 2 because of just budget limitations? And I get that, we can all sit here and like tell you what you should have run and how many runs you should have done. But did you just stick to 2 sediment scenarios just because of the resources available?
Yeah, I mean, primarily also just not really knowing what reasonable projections would be. The model is quite quick to run, so I could very, very easily generate a whole wide range of
Yeah, right.
scenarios, right? But how useful is that? And so I guess I'm happy for feedback, right? If there are scenarios that folks are interested in running, let me know, and I could do that. These data are still coming in, like we're still working on core data. The project isn't finished, right? And so I think that we have definitely some latitude to I guess ensure that the results are interesting and useful to y'all. So.
Sounds good. Kevin, Jen Hyman had a question. Have you considered land subsidence in the analysis?
Yes, and it's not incorporated explicitly. I was having trouble tracking down a good spatially explicit value for subsidence. Like I know that there's a recent paper, a recent-ish paper that used INSAR and looking at subsidence rates, and I'll probably end up just using that. But I do think subsidence is really important, especially in South Bay, where we have seen that. And actually, I'm wondering if the variation in accretion rates we're seeing are actually due to subsidence rather than sediment availability or elevation and such. So, yeah, I think it's a great question. Something that we're going to try to get local measurements of as well. So with our Sept network, we're going to do repeat measurements of their elevation, long-term occupations. And so, over say maybe 5 years or something, we'll have an estimate of, okay, what is the local deep subsidence rate for the various marshes.
Go ahead, Jen. It looks like you wanted to ask further.
Hi, yeah, I just wanted to mention, I'm Jen Hyman, the senior engineer from BCDC. One project I've kind of had my eye on is the Searsville Dam removal project that, if it actually moves forward, would release a whole bunch of sediment into the South Bay. And I just wanted to mention that I don't know how the volumes of sediment from that project compare to some of the needs, but I think it's an interesting project.
Oh, that's really great to hear, and yeah, absolutely. Letting the water flow free as much as possible, and bringing that sediment in. That's I think that's going to be key for longevity. Thanks.
I have a question for you. I'm curious. I was really interested in your carbon data, and like, how does that compare to other places you've studied, like in the North Bay? I mean, it's really super unique to see those high numbers in the South Bay, I guess. That's my question.
Yeah, I mean, I think so. I need to look again at John's data, at his results for other areas in the Bay, but I feel like these values are a little higher. I think just because of the bulk densities. Yeah.
Jim, question.
Yeah, hi, Kevin. Yeah, I really appreciate your presentation. There's a kind of a long-running observation that we've been doing in Lower South Bay. We can see like tremendous edge erosion that you kind of mentioned along Alvisa Slough, along Lower Coyote Creek. I call them mud chunks that keep falling off the side of the shore, and yet the contour of the creeks has not changed since like 1857, because you can look at the USGS maps from way back then, or whichever agency did those maps. It's always led me to kind of a pet theory that it's kind of like a mud glacier, that basically the marsh is accreting tremendously once the plant's established, once the alkali bulrush and the spartina and pickleweed they're more right at the water line. And the center of the marsh is more defined by alkali bulrush, and then when you get into fresher water, California bulrush, which grows very, very densely and pulls carbon from the sky, of course, and then creates root mass, and then basically it's growing vertically, the marsh, the center of the marsh, but it's constantly pushing outward because it has nowhere else to go. It can't really go much higher than the upper limit of tidal height, or above mean high tide. And so we get this phenomenon, especially every spring, where we see giant mud chunks flaking off the sides of the channel and dissolving or mixing into the water. In other words, the marsh is creating a sediment supply that then gets swirled around in Lower South Bay and eventually ends up deposited in some of the lower lying areas. I'm kind of rambling, but I'm sort of wondering to what extent, or if you're noticing, like, part of this phenomenon in the lower South Bay of tremendously more sediment than anybody ever estimates, and it keeps showing up. I believe it's auto-generated, and it's part of this this mud glacier effect is what I'd like to call it. That's my question.
I really like that. I love the mud glacier, and yeah, I mean, I think that it probably speaks to why we have such trouble getting good dates in South Bay, right? The sediment is just constantly getting reworked, and so I guess my hope is that perhaps with a more resolved model that can handle lateral processes, we'll get a better sense of that. And but ultimately, I think having some good observational data. I don't know, I'm trained as a field biologist. My go-to is like, let's get more data. So as much as I enjoy the modeling, I want it to be based in some sort of reality, ideally long-term measurements. So yeah, I think that'd be really interesting to look at further.
Go ahead, Jen.
As you're, thank you so much for your work on this. As you're probably aware, there's some studies by AECOM and Deltaras that show that the geometry of the South Bay right now causes the tidal datums to be higher than in the Central Bay. But in the future, with the salt pond restoration, that may change, and because the geometry of the South Bay could potentially get larger, and I'm wondering if you're in your current and future projects, are you going to take that into account?
Yeah, no, absolutely. The model is pretty flexible to that, and I've run up in the Delta, have run simulations like with varying tide range, right? And so that's essentially what we're talking about. And yeah, absolutely, I can pull in projections from Deltaris and other other models to help inform what the future might be. Yeah.
Nathan, go ahead.
Nathan with San Francisco Bay Bird Observatory. I work on a lot of the water bird habitat use of the South Bay. I'm curious about kind of the context for these changes, which are at like point scales, in terms of a lot of what you discussed was kind of the lower limit is kind of them transitioning back to just mud flat. Is that correct?
Yeah, right. So the how the model is formulated is, if you're at a high elevation, okay, your pickweed, as elevation declines, there's an assumption that you're going to transition to cordgrass first and then unvegetated mudflat. And that's just based on kind of current observations of where the vegetation is.
So I guess, yeah, my question is, I'm just curious about how much of that is an issue, because it's a lot of the tidal marsh restorations become like over vegetated for a lot of bird habitat use, at least, because like a mosaic of mud flats and open and denser vegetation is desirable for maintaining the diversity of species. But I was curious if you could touch a bit on like how this plays into or might inform the overall mosaic of these habitats at the more landscape scale.
Yeah, no, it's a great question. And I think right now at least in the current formulation with the Wendy, I'm a little limited in exploring the mosaic completely, and also I didn't incorporate projections of the restorations, which I think it's really going to have an opportunity to have a more diversity of habitats, a range of veg densities and stuff. So I think it's a really important question, and something that I'd like to explore further, especially as more sophisticated models kind of come online. And for instance, like I'm working with that 3D framework and want to get into more spatial distribution of vegetation. So rather than just modeling veg at a single point, okay, actually trying to get at more spatial connectivity, patches, and such, right? A bit more sophisticated kind of approach. So not there yet, working towards it, but I think, you know, I do think it's a good question because, yeah, even if there's not enough sediment for everything to be a high tide marsh platform, like maybe that's okay because it actually would support a more diverse array of wildlife.
Mm-hmm. Cool, thank you. Great talk.
So Kevin, there's a question from Ava in the chat asking about the chemical composition of the sediment and how that the bay slough water is relevant to the model. For example, thinking about saline water and the shrinking of clays or accretion, or how that's related to accretion.
Yeah, that's a very interesting point, and yeah, absolutely. I think that the process of I guess soil salinization and also just compaction, but through evaporation, right, and shrinking of clays. I think, yeah, absolutely, that could very likely be the reason why we're seeing such high bulk densities and relatively low accretion rates, considering how much sediment is there. But yeah, definitely something to look into further, I would say.
Great. Any other questions for Kevin? I just want to put in a plug for Kevin and Karen's team that are doing not only work in the South Bay, but throughout the estuary, looking particularly at sediment accretion and elevation change using SETs. So they have a huge network. Maybe you could speak a little bit to that work, Kevin.
Yeah, we've installed and have been monitoring sets now. You know, like I mentioned, the 20 that were just installed, but we also have sets all across the North Bay. And you know, we're working closely with the WRMP to continue monitoring of those. And yeah, we're really exciting to finally have I think a good network across the entirety of South Bay, or entirety of the Bay through the Delta. I think and we just need more time. That's the thing. We
More
should have
time, more
installed
money, more data.
yeah. You know, we you know, John Calway had put some the early version of sets out. I'm not sure when those were installed, but a while ago. And I think we do have kind of intention to go and try to revisit some of those if we can, just to try to fill in some of these long-term gaps in data.
Great. Thanks. We have time for maybe a couple more questions. So Ellen, go ahead if you want to.
Oh yeah. Hi. I think Karen Thorne. Hi, Karen. Answered my question, but it was more an elaboration on the, I'm very interested in the subsidence role. And I asked Kevin for a citation for the ANSAR report on subsidence. And I think it looks like in the chat, Karen Thorne gave me a citation for science.org and another one. Is that correct?
I believe so. Yeah. So those science papers, or those, yeah. And then, yeah, Christina also put in some papers. So I'll have to click through them and ensure that they're the right ones. But I'm pretty sure that
Okay.
sounds
There was
right.
another one she mentioned, Zanato.org.
That's just going to be a more of a database or a record of some data, I think.
Okay.
Perhaps that's actually the spatial data that I'm after, which would be neat. So
Okay. All right. Good. Just to clarify that. So I'll save these links in the chat. Thank you. Excellent presentation. It was really, really great. Really good.
And Ellen, there's a couple more. Jim Irvin put some information into. So.
Oh, great. Okay. Thanks, Donna.
Yeah.
Thanks for doing this, Donna. This is wonderful.
Awesome. I hope you enjoy it. So that's such a great segue for me. I just want to first off thank Kevin and Karen as well. I know they were both involved in helping pull this presentation together. We are hoping to do these on a monthly basis on different topics that are related to the science work of the South Bay Salt Pond Project. So look forward to more announcements for talks next month. I believe Gavin at HT Harvey and Associates will be talking to us more about sediment and quality assurance programs and some work that we're doing to try to find more sediment to be able to use in some of these restorations. So anyone else on the project team want to weigh in? I just want to say this has been really fun today and I've learned a lot. So yeah, thank you.
Hi, this is Dave Halsing. I just wanted to echo what others have said. This is our sort of our first foray into this new way of doing our science symposium. And I'm really grateful to Kevin for being our, I don't know, our grand unveiling of the new approach. And thanks to all of you for participating, and Donna and Ariel for making this all happen. You know, this is I think a good way to get more frequent, smaller bites of science out into the world. So yeah, thanks again, everyone.
Great. And do look on the website. We'll be posting the slides as well as the recording for this talk. So you'll be able to, if you have more questions, look at those. And if you want to reach out to Kevin with some data or ideas for modeling, I think they'll be really excited to hear from folks.
And Donna, I'd mentioned in the chat as well that I'll be able to send out an email to the attendees of this meeting to let them know when those are available on the website. And I assume everyone knows, but just FYI, if you click the 3 dots at the top of the chat, you're able to save the chat to get those citations and links.
So thank you, everyone.